Hello and welcome. Today we're going to be talking about closed path integrals of 1 over z, or functions of that form, and functions of similar forms, and integrals with branch cuts. Alright, so as we know, things like log or functions z to the 1/2, things like that involve multi-valued, I should say lowercase log, multi-valued functions, meaning they have multiple outputs, but they also have multiple inputs that lead to the same answer. So at least with the case of log. So we have to always worry about that. And now when we're talking about contour integrals, contours must, let me rewrite my state. Contours must stay within a branch cut. Oh, say, for instance, if I take complex log, like so, z, and that's going to have, theta has to be between, it has to be less than, or it has to be strictly greater than pi, and strictly less than, or sorry, strictly greater than negative pi and strictly less than pi. So we can draw that as so. And we usually draw it by just kind of putting a little kind of darkened area there, saying that that part of the complex plane is off limits. And so theta has to range between that. Okay, so that means that if I have a contour, if I have some contour in the plane, whatever it does, if it goes around like that, but it can't cross this, it can't cross that boundary. And if it crosses that boundary, what happens is, of course, then the multi-valued nature of the function will take over, and it can be it's ambiguous. We if I start on this side of the line, and I'm within this range, and then I move all the way around, and if I cross over, all of a sudden my theta value. So here, theta value is within this range. But now, so that's there. But then here, theta is clearly, as I cross over, theta is going to be greater than pi. And that, of course, is a problem because our log function can't take that value. And so similar things happen with the square root function. We have to take branch cuts for all of these functions in order to make them have a single value. So as we do contours, we're going to have to watch that. So let's go to the classic example of how this works, which is to take path integrals involving, I'm going to take a path integral c involving a function z to the a minus 1 dz, where a is non-zero. For now, we're going to say it's non-zero, and we're going to take a to be a real number. Okay, and we're gonna explore the case when a is 0. So when a is equal to 0, right? Of course, we have the integral becomes 1 over z, and we're going to approach this question of what happens in this particular case in a second. But right now, let's look at this function, and we're going to take c to be the path, be a closed curve. We're going to take it to be smooth. It'll be a circle. Now it's going to be of the form z of theta is equal to r e to the I theta. And theta is going to range. Okay. And so what is theta going to range from? We're going to range theta from all the way from negative pi all the way up to pi. Okay, so let's get a graph here of what's going on. And okay, so we're r distance away, and we're going to start here, all the way at theta is negative pi. We're going to go around like so, all the way over to there. All right, and we're going to be taking as our branch for this to be the negative real axis, which is that's our branch. Okay. But let's rewrite what z to the a. So we know that complex exponents or real exponents that we can write z a to the negative 1, or a minus 1, I should say. We can rewrite that as e to the a minus 1 times, and I'm going to take the principal log of z. Okay, so this is really the function that we're integrating, and of course it contains log, and we're going to take the principal value branch, which corresponds exactly to this branch cut there. So the question arises then, what happens when, if I'm going to do this integral, theta is going to start at negative pi, and then it's going to go all the way to theta is equal to pi. So this log function is log's domain is negative pi strictly greater than theta, or oops, all the way to pi. So so at theta is equal to negative pi and theta is equal to pi, the log function of z is equal to natural log of r plus I theta. But we already know that these two values are the same point. They're the same point in the complex plane. They're the point that's right there on our branch cut. But our log function is different values. At theta is equal to pi, and theta is equal to negative pi, right? And they're not, and that's why they're not allowed into the domain of log. But the idea here is if I take log z, and I take the limit as theta is going to negative pi from the positive side, we can see that that's going to equal natural log of r plus, minus I pi. But if I take the limit as theta is going to positive pi from the negative side, it's going to be log z. It's going to be natural log of r plus I pi, which these are clearly not equal. But clearly this function is continuous there. As I take theta to be close to pi or negative pi, the function itself is locally continuous. Oops. I got to find a way to stop that. Sorry, guys. So clearly it's locally continuous here. So if I'm coming in, if I take a small neighborhood around that point, every path I take going into that point is continuously related to that point. And likewise, if I come this way, it's continuous going that way. So we're gonna just see what happens then as we move forward. Okay, so let's try going and computing this. So we're gonna try doing this. So again, our path c is going to be r e to the I theta, and theta is going to range from all the way from starting at negative pi and going all the way to pi. All right. And our z a to the negative 1, or z to the a minus 1 power, apologies there, is equal to e to the a minus 1 times the principal branch of log of z. All right, and so and we can write that now. And then of course, so this is our z of theta function. So in order to write this integral out in explicit form, we're of course going to have to find z prime, where now this is taken with respect to theta, and that's of course going to be r I e to the I theta. Okay, and then we have to evaluate. So that's with respect to theta, and then we have to evaluate our function on this path right there. So this becomes integral from negative pi all the way to pi of f of z of theta times z prime of theta d theta. That's now the constructive integral that we can actually compute, negative pi to pi. And this becomes e to the a minus 1 times, we have to put in there, and the log function of z of theta is, we put that in, r e to the I theta is going to be natural log of r plus I theta. So I put that in. Likewise, and then I have to put z prime, and z prime is right here. It's r times I e to the I theta d theta. Okay, let's continue on with this integral. I'm going to call this integral, and I'll put a little a there. That'll be just my label for it. All right, so a little aside here, e to the a minus 1 times natural log of r. We can break this thing up into little pieces here, and e to the a minus 1 times I theta. That's just breaking this into pieces here to different factors. And of course, this factor right there, that becomes clearly r to the a minus 1 when I put it back down in exponential form. And now we have e to the I a minus 1 theta. All right, so now when I multiply this through, then we're going to get the next bit here. We have a r a minus 1. We see there's another r sitting there, so I'll put that r next to it. We have an I that's coming right there. And then finally we have an e to the I a minus 1 theta times, and then finally this piece right there, e to the I theta d theta. Okay, we're getting close. We see an a minus 1 there, and then a power of 1 there. So that becomes, and this of course doesn't depend on theta, so it can come outside the integral. So we have an I that also can come out of the integral. An r to the a power. Okay, that works fine. A is not 0, so we can work with that. And then, well, even if a were 0, it'd be fine. And then finally, and then we see we have this here. We can sum those two together. And we get an e to the I times a theta, because there was a plus 1 there and a minus 1 there, right? That becomes d theta. All right, so this is dramatically simple now, or more simple. And then we can take an integral of this. So we learned earlier that we can actually just take the antiderivative of this, and so that becomes 1 over I a times e to the I a theta, all evaluated at negative pi to pi. So we can write this down as I r to the a all over a. I'm going to keep that I around there for a second. I'm going to multiply a 2 there and a 2 down there, and note that this is e to the I a pi minus e to the I a pi, but we have to make it a negative. Of course, this part right there looks like sine. Well, it is sine of a pi. Okay, so we can write this further as I times 2r to the a power all over a times sine a pi. Again, now this is the result of this integral. And again, this is a closed circle, so we can, what we're writing here is this circle. It's a closed circle around there. And it starts at that branch cut and it goes around. So it's positively oriented, and it's a closed path. Okay, so it's a closed curve in the plane, or a closed contour. All right, so there's our result, and now let's try. We got to analyze this result here. Okay, so I'm going to go to a next page here. So let's rewrite our result. IA is equal to the integral C, this closed contour, z to the a minus 1 dz. And we found out that was equal to 2I r to the a power all over a times sine a pi. All right, so first of all, if I take a to be equal to plus or minus 1, plus or minus 2, plus or minus 3, and so on and so forth, and what we're writing here is n is not equal to 0, because if I make a to be equal to these integers, right, that would imply then that sine a pi is equal to sine n pi, which is always 0. Okay, so now we have a neat result. We have the following. This is a closed path. A closed path of any radius r, okay, of z to the n minus 1 dz, provided n is not equal to 0, that's always going to be 0, because sine n pi is always 0. All right, so what about the case now of n equals 0? Let's look at this case. What's going on there? Well, what we see here is what we have is, or I should say a is equal to 0. Let's go back to the original constant. Let's not change our constants. Well, we can't exactly, because there's that division by 0, we have to now compute a limit. So what I'm going to do is take my limit of a going to 0 of 2I r to the a power of sine a pi all over a. So first of all, limit, I should put this over here. That's all over a. Limit r to the a going to 0, that's going to be simply 1, okay? So we don't even really need to bother with, I can rewrite this as limit a going to 0 of 2I sine a pi all over a. What we have here is a 0 over 0 condition. This is so this is a candidate for using L'Hopital's rule. So we can rewrite that as limit of 2I, a going to 0 times, and we take the derivative of the top, and that's going to be pi times cosine of a pi all over the derivative of a, which in this case is just 1. Okay, and so of course cosine of a pi going to 0 is simply 1 as well. So we see the result then is just this stuff right there, and that 2 pi I. So now we have a very famous result. So what we have then is the integral along a closed path of any radius. That's our c of 1 over z, which is of course what happens when a is 0. dz is equal to 2 pi I. However, the integral of the same closed path of z to some other integer, call it n minus 1, where n is not equal to 0, dz, they're all 0. So that is a really important result, and that's going to be used very frequently in the future. And so please log that away in your memories. So again, this is a closed path around 0. It's a closed circle of any radius. And so we'll be talking about, I should say, closed circle. and we'll be using this result frequently in the future. So the only power of z that yields any non-zero result from the integral is 1 over z. All the other integers, and that means any integer, any power of z other than the 1 over z will yield 0 as the closed path integral result of a circle of any radius. Okay, so thank you very much.